Hi everyone. So to introduce myself again, I'm Lenny. I'm from Ravelin, and we do real-time fraud detection. And the type of fraud we typically look for is credit card fraud. So any merchant or any company that accepts credit cards online, we can work with to try and protect them from fraudsters. We've been around for about 3 years now. We've raised about 5 million for some really reputable VC companies, and we've got a team of just under 40 people. And we work with quite large companies in Europe and the rest of the world. Just a bit of background on fraud itself. So fraud's actually quite a big market. About $16 billion of revenue is lost to fraud. I think that was numbers from 2015 or 16. And it's growing rapidly. 25% year on year is the number of fraud. And actually, it's very easy to become a fraudster. So you can go onto the dark web and you can buy a stolen credit card number for about $1. And it's such a mature market that the person you're buying it from will actually give you a money-back guarantee if that stolen credit card doesn't work. And most fraudsters aren't sophisticated fraudsters. They're typically students or teenagers, and they see it as a victimless crime. And to be honest with you, in most cases, the police won't do anything about it. Unless you're defrauding someone in the region of tens of thousands of pounds, typically 50, 100 pounds here and there, that comes from the merchant's pocket, the police aren't really going to get involved. And the London Met the Met in London have about 5,000 cases of fraud reported to them every single day. So there's a huge amount of fraud in the world. I've got this slide up here just to show you the markets we operate in. So we are truly a global company. And the reason I want to show you this is because the fraud in different countries look very different from one another. So fraud in India, for example, is going to look very different than fraud in Ireland. So we have to cater for those needs when we're building our models. Cool. So how does it work? What happens is a merchant will sign up to our service, and they will start streaming data into our system. And that will be user data, so it could be credit card registrations, it could be item details, i.e. how many items are in the cart, the value of the cart. It's even the items within the cart itself. So for example, we work with food delivery companies, and if you order 7-Up, you're more likely to be a fraudster than if you order Coca-Cola. Just a tidbit out there. But all of this data comes into our system, and it comes into our API, and we give back scores in real time. And the word real time is an interesting word, because when we first started out and we first started talking to issuing banks and merchants, the amount of time they thought it would take us to predict whether a user is a fraudulent user or a genuine customer was about 20 minutes. And that was because the industry average was about that long. So they didn't use machine learning. They typically had analysts that sat there looking at every transaction that comes in. They had a load of rules, and they flagged up ones that looked suspicious, and an analyst would work through a queue. So when we told them that we were aiming to do it in about 200 milliseconds, they were taken back a little bit. So what happens is the API requests come in. We have a graph network. We have some blacklists, and we have machine learning, all to try and predict fraud. And then we respond back to the merchant in real time. And we do this typically in the checkout flow, so it's very quick. The focus of this talk is obviously going to be around the machine learning side of things. So within our infrastructure, we run microservices. And we have about 50 Go microservices across between 70 and 100 servers, depending on how busy we are throughout the day. And we also have one Python service. We've named that service Justice, and that will be the vast majority of this talk. And Justice is our machine learning service. And it's less micro and more macro, which you'll see in a bit. And we use Protobuf to communicate between services. And Protobuf is just an encoding format, but it comes up a little bit later in this talk. And we predict on any given month about 100 million, we make about 100 million predictions every month, and that's an average month. And we make less predictions between 3 and 4 in the morning than we do at 7 in the evening. So during our peaks, we predict about 1,000 to 2,000 times a second, and during our troughs, we predict maybe 1 or 2 times a second. So it really depends on the time of day. I've just put this slide up here. This is kind of a catch-all, so this is all the technology we use. We have got a blog post out there if anyone is interested, which lists all of the technology and the reason we use the particular tools. We're a company that believes in using the right tool for the right job. We also believe that we need to be able to scale, and we need to be able to build our system in a fashion where we have redundancies built in. So we can go into our infrastructure and pretty much destroy any single server, and it should come back up online and heal itself and provision its own code. And for the most part, it works pretty well. So this is just another slide to reiterate that point. So every box there is a service. This is just a snapshot of a small bit of our infrastructure. And so there's a lot going on, and the bit that I'm going to talk about now is this bit down here, which is the machine learning models, and that's the brain of our system. So you can see we've had to build quite a lot of stuff just to kind of cater for machine learning. And obviously, it's a lot of business requirements and things like that. Cool. Another belief that we have is that we want to be able to build and push code and models in the same way across the business. So we want our developers to be able to build and deploy code in the same way that we want our data scientists to be able to train and deploy models as well. And this is what our pipeline looks like. So we have a local dev for the engineers, and for the data scientists, we have large VMs, which we spin up and spin down depending on their workload, and they SSH into those. And we use Docker for that, for both local and for the VMs. We then use a service called Circle CI for all our building. So this is when we want to build a Go service into a binary, we'll use Circle CI to do that. But also when we want to build Justice, our Python service, or any of the models, they go through the build process, and we'll have tests around that. And then we'll get an build artifact, and we'll push that onto S3. Then we curl this endpoint. So we call an API endpoint to tell our provisioner, Atlas, to go and deploy whatever we've asked it to do. So Atlas, there's a few steps here, but Atlas will go check that the artifact is in S3. We'll pull it down. We'll run that artifact. We'll health check it. And then as long as everything's good, it will deprovision the old one. For the models, there's a couple of additional steps. We run our models in what we call dark mode. So dark mode is where a model will get exactly the same traffic as the existing model, but it will just log the results of that model into the database. But we won't actually reply back to clients with our predictions using the dark mode model. And this is just a last step to ensure that we really do have a good model out there, and we haven't screwed up in some fashion by missing an important part of the data. The reason we do this is because for most of our clients, if we screw up, it costs them a lot of money. We deal with very low margin companies. Typically, their margins are in the range of about 5 to 6% of the total revenue. So one fraudster that gets through will cost them all of their revenue plus the fees that Visa or MasterCard incur onto them for actually allowing a fraudulent transaction to go through. So one fraudster could equate to anywhere between 20 to 100 genuine customers. So we really do need to be sure that our models work. And once we're happy with the results for dark mode, then we promote it into live. Again, that's an API endpoint. You call it, and we can set a certain amount of traffic if we want to, but most of the case, we just switch it straight over. Cool. It's quite small here, but this is a command line utility, and I just wanted to show how it works. So we call it RShell for Ravelin. And you can, once you're logged into an environment, you can ls, and it will give you the endpoints of a particular service. This is us deploying it, so it says deploy integration test service. This is the version, and then this is the language that it's in, and it will go through all the steps and deploy everything for us. And then finally, this is just calling an endpoint itself. So this would be an example where you could call Justice and say, hey, we want to move the dark mode model into live and give it some parameters. And again, I want to show you the slide because I want to show you that I want the tooling to be the same for data scientists as it is for engineers. Cool. So, Justice, our machine learning service. So you're about to see the steps we've taken over the years to get Justice to where it is yesterday. So I only have the results from 24 hours worth of our version 3 running in production, which I'll show you at the end. So, Justice 1. 3 years ago, it was pure Python. We trained a model and we pickled it. So Pickel is a way to serialize a model, and then you can pull it down and turn it into a Python object. So we pickleize it, we put it into S3, and then when we want to deploy a new model, we tell Justice, hey, we have a new model, go and get it from S3. And Justice itself will go to S3, pull down this pickled model, unpackage into memory, and then we can start making predictions with that new model. The problem with Justice 1 was the upgrade process of Justice itself was quite difficult. So we had to build and we had to gzip it. So unlike Go, where you just create a nice little binary that's a few megabytes in size that you can ship around, with Python you ended up with hundreds of files which we had to gzip, put onto S3, and then therefore Atlas, our provisioning service, had to have different rules for Justice than it did for the Go stuff. But it was okay, and it unzipped it, it ran Flask, and then it health checked it and all the rest of it. But we also had something called a sidecar. So a sidecar is called a sidecar because it sits alongside the main bit of software. And it enables all of the other services to talk to Justice through this sidecar. And the sidecar was written in Go. And the reason for that was when we deployed a new Justice, we had 2 Justices running. One which was being health checked to make sure it was okay, and an old one. And so we needed that sidecar to be able to know the difference so it could flip the traffic between the 2. So it's just another step that complicated matters. And the main problems we had with that is there's potential for runtime errors, because if we had 12 Justice boxes, servers running, and we told Justice to update the model, if we ended up with one service not doing it, when we tried to make predictions with this new model, it would crash or it would fail and we'd get runtime errors. It's single-threaded, which was our fault for writing it in a quick startup-y way, but anyway, it's single-threaded. CPU utilization was low, so it needed a lot of memory. And to have a lot of memory on Amazon or GCP, you need to buy a number of cores. You can't have one core with a load of memory. You have to have 2 cores or 4 cores with a load of memory. So there was low CPU utilization, and the code was quite complex. So that was V1. Cool. So I've got a little table of the things we're trying to achieve here, so everyone can keep track. So quick builds, quick model deploys, but pretty much everything else didn't work too well. So Justice 2. So Justice 2 was introduced about 9 months to a year afterwards, after Justice 1. So we'd grown a bit, we have more traffic coming in. This time we thought, we know what to do. We'll use containerization. That's been around for a good year now. That's going to be pretty solid. So we chose Rocket instead of Docker. And the reason we chose Rocket is because Rocket you can run like a binary. So we thought, good stuff. It's going to be just like Go. We'll put this Rocket there and we'll run it and everything will be wonderful. And so we baked the models into Justice itself. So no longer did we deploy models separately from deploying Justice. The whole thing was deployed in one go. But we came across quite a few problems. So pulling down the containers and unzipping, we saw big CPU spikes. And to be honest with you, we would have seen them in V1 as well, but because we had less traffic in V1, it wasn't as noticeable. So it wasn't as noticeable as when we switched to V2, we had a lot more traffic. Insanely slow to build the models. So a data scientist would train a model and we'd try and build it, and it would take 40 minutes to build. Which those of you who come from a C world would think 40 minutes is nothing, but people who come from a Go world expecting it to compile in 30 seconds, 40 minutes is a long time to wait. And it ended up being massive. I mean, gigabytes in size. We have to ship around all these things. The startup time was also an issue. So it was initializing the models in Python. And again, that took the best part of 5 minutes. And when we're starting to see traffic go up and up and up, and we need to provision more servers, 5 minutes is a really long time. They had to hash the whole, they had to check the hash to make sure it had the whole thing, and it has a 2 gig file, so the hashing took a long time. And deployment, provisioning time, caused autoscaling to be slow. So when we had those peaks, it was a bit of an issue. And you can see from here, we didn't do a great job with version 2. So we effectively lost quick builds, quick model deployments, but we got some simple justice deploys, and we got runtime protection, but not great. So Justice 2.5, this didn't deserve a brand new version number because we were just trying to get back the first 2 ticks. So we did a lot of work around that. We tried Docker. Docker didn't give us any additional benefits than Rocket. So we saw exactly the same problems with Rocket, but we then introduced complexity with the provisioning service. So with Docker, you have to run an agent on the machine, which means that Atlas had to talk to that agent as well as just provisioning the code as well. So it's an additional step. We switched from Pickel to JSON, and this was to decouple the execution code from the parameter file. So this is important because if you want to do a library upgrade, then if you use Pickel and you pickleize the objects, you need to re-pickleize all of the models to be able to use that library upgrade. When we decouple it with JSON, it gives us more flexibility around the parameters. So we can read that in, and then we can decide which version it should run against. We tried Kubernetes. Again, that didn't really give us any improvements, and we still see the same problems. And we still have exactly the same problems as we did beforehand. So we tried all those things, and we ended up like there. So we're still not doing. We've almost got all of the ticks there, but just not in the same version. And I put a cross next to simple justice deploys, but the guys at work seemed to think that it deserved half a tick for certain reasons, because it was marginally not as bad as it was in V1. Anyway, so we're getting there. But V3. So V3, before I talk about V3. So this is something that you definitely have to be aware of. If you build your machine learning pipeline or your prediction engine to run on a single core, but it uses a lot of memory, you end up with a problem of not being able to auto-scale. And I'll explain. So Justice uses 1 core on a 4-core machine. We auto-scale at 50% CPU utilization. In most cases, you want to auto-scale about 70% utilization. But because of the slow times to deploy code, we needed to scale sooner to be ready for when the traffic was at 100%. The problem is it never hit 50%, because even if it was using 1 core at 100%, that's only 25% of the box. So we never auto-scaled. It just wouldn't happen. So that's the first problem. The second problem is when we deployed the code, gzip ran, and it used 100% of another core. So all of a sudden, our average CPU was above 50%. And so then we would scale. And then when we scaled a new box, we would do a gzip on it, and we would run justice, and then we would scale again. And then it would again and again and again. And so we just ended up in a loop of scaling whenever we provisioned justice. So this is a pain in the ass, and this happened. We realized this around November. December was our busiest month. And we tried everything. We tried C groups, we tried nice, we tried containers, we tried everything to try and stop gzip from using 100% CPU utilization. We couldn't get it. So we just decided to throw money at the problem. We just over-provisioned for the whole of December and just didn't touch it at all. Because what's money? It's like, doesn't matter, right? Cool. So Justice 3. Here's the light at the end of the tunnel. So we switched from Python to Golang, which isn't a commonly said thing at a machine learning meetup. And we were able to use all of the cores on the boxes because we use lightweight routines, lightweight Go routines. We switched from JSON to Protobuf. So Protobuf is a serialization format. I think it's from Google, but it's very compact. So our model shrank from about 40 megabytes down to about 130 megabytes. And that's a decent enough cost saving that you notice it when you're starting to push these files around. So we saw faster deploys. We saw less CPU unpacking when it came to unpacking the JSON versus the Protobuf, and you get more strictly typed parameters in your files. The build size have gone down from about 2 gigabytes, granted that was with the models in them, down to about 16 megabytes. So it's again a huge difference. We can start shipping binaries around like we do with the rest of our infrastructure. Memory usage is about the same. It's got to hold the models in memory, so not a lot you can do about that. So how do we know that? So we develop in Python locally, but we run predictions in Go. And that is recipe for disaster. But we have these 50 tests, which we run every time we deploy a new model. And hopefully that's enough. So I say hopefully because it's only been 24 hours. So I don't know whether it's going to work forever. And finally, there's no sidecar. So sidecar's gone. We can use the library you use for the rest of the service. So we can use all the existing tooling. We can use our existing deployment, scaling, all the rest of it. And we have the domain expertise in Go, which has really helped. So finally, we actually end up with V3 where we tick every single box. After 24 hours, yeah. So just a little bit of information about the models we run. We run random forest and neural nets, and that's it. So we don't run anything else. Sorry, random forest. And so we wrote the library for the random forest because it's quite simple to write. And the neural net, we're going to use TensorFlow. We actually use Casa at the moment, but we're going to switch over. We've seen at least a 4 times throughput, but that's because we're using all the cores. And we're now seeing twice the speed, at least twice the speed, so a reduction in latency for every single request that goes in. There is a caveat. We do see slower batch operations in Go. And that's because behind the scene, Python has matrix operations, and it has a switch statement. If it's a batch job, it uses the matrix operations. If it's a single job, it will use a normal serial path. While Go, we use lots of Go routines. So and we don't use matrix operations, so it's a bit slower. And this is a graph that I literally pulled out a few hours ago for the last 24 hours. And so this is latency. And at the top, you can see the old Justice, which is the contained one. And so the blue line is the medium. The yellow line is the 95th. And is that purple or blue? Purple line, the one in the middle, is the mean. And so if you have a look at the 95th, which is probably the most important one, you can see it's about 70 milliseconds per prediction on the top graph. And at the bottom, you're seeing it closer to 35 milliseconds per prediction. So it's a significant improvement for us. So in conclusion, so what next for us? We're potentially going to move to multiple services per model. So every model will be its own service. We're still undecided about that. But one of the advantages for us would be that we could then have a GPU class of machines for the neural nets and just the normal CPU and memory machine for the random forests. We're going to explore Kubernetes again. We're going to move from, I can never pronounce that, Keras to TensorFlow. And then I heard this quote from one of the data scientists today, so I think we might be done. So we'll see whether his prediction lasts. But in conclusion, I think it worked for us because we brought Justice into a domain of expertise. So we're very good at running Go in production systems. And we haven't had a huge amount of experience running Python in production systems. And I have no doubt that you could have done all of this with Python if you have that domain expertise. Cool, that's about it. Just one last reminder, we are hiring, so if anyone is interested, then there's a AngelList page, and those are the positions that we've got open. Thank you.